Good morning, good afternoon, good evening, good day, good whatever, physics friends. Sean Nally here. I am so glad to be with you today. Our special business of the class is going to be all about the reflection of light. Now, when we last left off, we were talking about the electromagnetic spectrum. I hope you remember the electromagnetic spectrum, our old friend, the EM spectrum. That was a list of electromagnetic waves, generally speaking, starting from low frequency and going up to the highest imaginable frequencies. And that went in order from radio waves to microwaves to infrared, and then a little sliver called visible light, ultraviolet light, X-rays, and gamma rays. And again, low frequency to high frequency, or if you prefer, long wavelength to short wavelength. Well, we're going to really talk a lot about that little sliver, the visible light, because that is, of course, that's where all the action happens as far as your eyes are concerned. That tiny little 400 to 700 nanometer range is the range in which our eyes have evolved to be sensitive. Not surprisingly, because that is right around the peak output of the sun, and we are, evolutionarily speaking, day hunters. So it is, of course, most advantageous for us to be able to see in the visible range. If you had been born a honeybee, you'd have a little more low UV sensitivity, for example. Okay, so we're going to talk about reflection of light first of all, and then we're going to get into several other properties of light. Now, reflection of light is incredibly interesting, and it makes a lot of very, very cool things possible. But we're not just talking about visible light. In fact, the things that we're going to be talking about for this new field, new for us anyway, called optics, is actually going to apply to pretty much just about every electromagnetic wave imaginable. Now, I say just about because, as it turns out, well, certain electromagnetic waves don't necessarily reflect off of all surfaces. They might just pass through those surfaces. However, they can interfere with different surfaces in the same way that I'll be talking about the reflection of light. So please understand that even though I'm using light because it is literally the visual way to think about this, everything I say is going to be at some level applicable to other electromagnetic waves. So, well, let's just jump right into it. You can see we've got a beautiful little image on the screen here. I wish I could say that I took that picture. It's really pretty, but notice that you have a beautiful reflection of the mountains into the water below. Okay, so let's talk about what's going on with all that sort of thing. So, what is reflection of light? Reflection of light is actually what you probably think it is. It's a bouncing. It's a bouncing off of a reflective surface. However, it's a bouncing that happens in a very predictable and regular way. It is a bouncing that is, well, let's say it's quantifiable. It is a bouncing that is related to the conservation of energy and indeed to something else we call the conservation of momentum, which is fancy speak for Newton's third law. So, there is a simple law. We call it the law of reflection. It simply says that the angle in equals the angle out, or if you prefer the angle of incidence, that's what we got over here on the left, equals the angle of reflection. Now, how do we measure these angles? We actually measure these angles with respect to something called a normal line, which is a perpendicular line. This red line right in here is the normal line, and the angle is measured with respect to that. Of course, we could measure if we wanted to with respect to the mirror, but as you will see, it actually makes more sense to measure with respect to a normal line for reasons that I hope will become clear shortly. So you can almost imagine it to being like a ball bouncing off of a wall, or a tennis ball bouncing off of a court, or billiard ball bouncing off of a rail. The angle in equals the angle out, and that's what light does. In this case, we're talking about visible light hitting a visible light wall, which would basically be something like a mirror. We think of mirrors as being reflective to visible light, and usually they're aluminized. In the old days, they would have been silvered or some other metal. But yeah, that's what you can see going on right here, is what we think of when we think of light bouncing. Here's another way to look at it. Incident ray, reflected ray, they are one and the same. Now here's some more details. Here you've got typical mirror reflection. I'm only indicating this with one ray right here. Of course, with light, we're usually talking about, oh my gosh, billions of rays. But let's just imagine one light ray, maybe even one laser beam, which in and of itself is made up of many, many light rays. But let's just say we have got a simple laser beam or a flashlight beam. The angle of incidence here equals the angle of reflection. Okay, and again, this is a conservation of energy type idea. The initial energy of the light is going to be equal to the final energy of the light. And also, the initial momentum is equal to the final momentum, momentum being mass times velocity. It's a little bit trickier for light because light does not have mass, but these laws are really what give us the idea of reflection. Angle in equals angle out. So you take a little bit of energy conservation and put that together with a little bit of Newton's third law, action-reaction, and you get the law of reflection. We call this specular reflection when we happen to have multiple rays of light. They come in parallel and they exit parallel. And over here, this one looks a little bit more confusing. This so-called diffuse reflection. These are, let's say, parallel rays coming in and then bouncing off of a bunch of irregular surfaces like maybe broken glass or a shattered mirror or a mirror ball or anything like that. But in that case, they look like they're going in different directions, but that's because they're actually hitting at different angles. Still, relative to each piece of mirror that it hits, the initial angle equals the final angle. The idea is always the same. The angle of incidence equals the angle of reflection. Again, always measured from a so-called normal line. Normal meaning perpendicular. Normal is the math word for perpendicular. Okay, let's take a couple of minutes and play around with this so-called light playground. I really like this because it kind of shows it very, very nicely. So we'll start off with a ray of light. We've got a beam right there. I'm going to grab a little mirror segment, and right away you can see the light hits, bounces, and if I put more segments in, it goes crazy. Now this is an idealized setting where there's no loss whatsoever, there's no absorption of the light from the different mirror surfaces. Not only that, but actually the mirror surfaces the mirror surfaces are mirrored on both sides, so I think you kind of get the idea right there. So if you get a chance, play around with that. It's a lot of fun. We'll come back to this when we start to talk about curved mirrors. It's also worthwhile to take a look at what happens if you do a beam of light. So this, you can see I can make a beam of light, and let's use a segment as well. Well, it's the same sort of idea. The light rays that go in at a certain angle, they bounce off at the same angle, and that is measured with respect to a so-called normal line. Each one of these initial rays would have a normal or perpendicular line relative to it. So this guy up here, the top one, bounces off. The initial angle of incidence would be right in there if I put in a little normal line, and it bounces off that way. And then this one is parallel, but down a little bit lower, and on and on and on. So I can put in another mirror. I think you can get the idea of what's going on right here. There you have it. Imagining it as a flashlight right there, angle of incidence, angle of reflection. Okay, I think I have made this pretty clear. It doesn't seem at the, I guess it doesn't seem really at the start of it that this could be all that complicated, right? Well, actually, it can get quite complicated when you have curved surfaces. So here it is sort of animated. Now, you don't just have to think of this as being, a single ray of light. You can actually imagine this as being waves of light that are going in and hitting a surface, bouncing off, and coming right back out that way. This model works whether you think of this as being a single ray of light or being waves of light hitting a surface. In fact, water waves will do the exact same thing when they hit the surface. Now, when light hits curved surfaces, that's when it gets a little bit tricky, and we will talk about that in the second part of the class video. Okay, stay tuned.